Welcome to section 10.2, applications of the second derivative. Historically, this has been one of the most challenging sections out of all the sections in Math 129. We're going to do three things in this section. First thing we're going to do is look at determining intervals of concavity of the graph of f. Then we will discuss inflection points, and then we will discuss the second derivative test. The second derivative test is just another test, like the first derivative test, to determine relative extrema, relative maxima and minima. Let's get started. So, in this page, on this slide, you're looking at the steps to determine intervals of concavity. Bottom line is, if we can determine the second derivative of some test value is positive, then the graph of f is concave upward. Here's a way to remember that. If the value of the second derivative is positive, think of happy face person, happy face. That's concave upward. Smile. If the second derivative yields a negative value, a value less than 0, then it's sad face. There's the negative and there's the sad face. This is concave downward. Let's look at some examples, shall we? Number 1, determine the interval or intervals where the graph of the function is concave upward and concave downward. Here is the process, and I hope you see the similarity in this process as compared to what we did in section 10.1. Okay, first move is to come up with the first derivative. So first derivative here would be what? 3x squared minus 1. And then, because we're looking at intervals of concavity, you have to use the second derivative. You have to come up with the second derivative, which in this case is 6x. All right, so after you've determined the second derivative, which, by the way, this can be a pain in you know what for some functions. This can be a challenge, okay? At this point, you want to let the second derivative be equal to 0 and solve for x. See the similarity here as compared to what we did in section 10.1? And then solve for x. In this case, we just get 1x value, 0. All right, at this time, we need to now look at the sign of the second derivative based on some test values. Again, do you see the similarity here as compared to what we did in section 10.1? I'll stop asking you that. Okay, so if x is 0, put a 0 there. Unshaded, because we're always going to use parentheses for our intervals. Parentheses always for our intervals. Let's come up with test values. Maybe a -1 and maybe a +1. All right, so what we're going to do is we're going to plug in a test value, a value on the interval from -infinity to 0 into the second derivative. Into the second derivative. Note, sine of f double prime, second derivative. So you plug in a -1 here, the second derivative, you get a negative. You plug in a +1 here, you get a positive. So what did we just look at on the first page? If it's negative, it's sad. So that means, therefore, the function is what? Is what? It's going to be concave. Let's do it this way. It's going to be concave downward. Where? Concave downward, sad. On the interval from -infinity to 0. And it's going to be concave upward. Happy. Happy, upward, upward. On the interval from what? 0 to infinity. That's example number 1. Example number 2. Oh boy. It just went up in difficulty level big time. And it did so because of the given function. The process will be the same, but these can become very challenging based on the given function. All right, so the process is the same. Let's see if we can do this. First step, come up with the first derivative. You have to use the quotient rule here. Quotient rule. So what is that? That's low d high minus high d low, and then low, low. And I'm going to reduce this. This becomes a what? This becomes, let's just rewrite the whole top. Let's rewrite the whole numerator. So we get 1 plus x squared minus 2x squared. So this would be 1 minus x squared on top, all over 1 plus x squared quantity squared. There's our first derivative. What's our second derivative? Well, fun times here. Second derivative. All right, you got to show me your work for credit. You got to show me the work. Okay, quotient rule again. Here we go. Low. There's low, the whole thing, times d high. There's the high. So the derivative of this would be what? Negative 2x, and then minus what? Minus what? Minus high. There's high. And then d low. Be careful. D low here requires the use of the chain rule. Isn't this fun? So differentiating the bottom here, the lower, would be what? Would yield a 2 times the quantity of 1 plus x squared to the power of 1. And then what? That's just the derivative of the outside, leaving the inside the same. Again, we're using the chain rule. Second step in chain rule is to differentiate the inside, which would be 2x. All right. Now, let's finish it. Low would be 1 plus x squared to the 4th. Okay, we got to be able to simplify this. So, Well, here's the deal. We could look at, let's see, what's happening right here and here. That's 2 times 2x. That's going to be a 4x. But we also have a 2x here. It's a negative 2x. I tell you what, here's what I'm going to do. I'm going to look for things that are in common and redo it that way. So I'm going to look at this as follows. I'm going to say it's the same as negative 2x. And I have one of these in common. So times the quantity of 1 plus x squared. And then what has to be left inside the brackets? I'm going to use brackets here. Well, I have what? The quantity of 1 plus x squared plus, let's see. I changed to a plus, right? Because I pulled out a negative 2x. So right here I have a positive 2x. If I want it to stay that way, then I have to make this a positive because I have a negative out in front, because a negative times a negative is a positive. Doesn't this make sense? Okay, so we have what? 1 minus x squared, and then a 2. Okay, that's what's left over in the brackets. I'd recommend, pausing the video, taking a look at this, and thinking about what you could pull out from both of these expressions. What could you pull out from both these expressions? And then what must be left inside of the brackets, okay? I'd pause the video and think about that, and then see if this makes sense. All right, let's finish the simplification by looking at what's inside the brackets here. So what's inside the brackets would be what? It'd be 1 plus x squared plus 2 minus 2x squared. Now, I'm using the word simplification, but it's really just the factored form of the numerator so that we can use it to actually come up with intervals of concavity if any exist. Okay, so this just becomes what? 3 minus x squared. And that's going to be all over this. Again, this is definitely more challenging. The algebra involved here is crazy. All right, so it's just going to take some time and effort. All right, but I really, simplification, okay, I'm using that word loosely, I guess. I am actually writing the numerator in its factored form. I did simplify several things in order to do that. But at this point, what we will do is we will let the second derivative be equal to 0, and we're going to try to solve for x. So notice that all I'm going to do is let the numerator part of the second derivative, the numerator part of the second derivative be equal to 0, and then try to solve for x. So when I do that, I need to recognize that 1 plus x squared, this is impossible for this to be equal to 0, so I don't worry about that factor. Furthermore, going back to this, it's impossible for this also to ever be equal to 0, to make this undefined, based upon this expression 1 plus x squared. So all I'm really focusing in on now is this, the negative 2x equals 0, or 3 minus x squared equals 0. So we would get what? We'd get x equals 0, and then solving this one, if you were to add x squared to both sides, and then take the square root of both sides, you get two answers, because it's quadratic, and those two answers will be plus or minus 3. Okay. Now, what we need to do is come up with our number line, look at the sign of f double prime, based on some test values. Okay? Again, this is a tough problem. I get it. If you have questions or concerns, you reach out to me. I will assist you. They're not all going to be this tough, but you could have one like this on the test. So be prepared. Okay? Work on your algebra. All right, let's finish this off. In this particular problem, we have 4 intervals we need to check. 4 intervals we need to check for concavity. The square root of negative 3 is about negative 1.7. So let's use maybe a negative 2. And then this will be a negative 1. X equals 1, and then finishing out with a positive 2. You're going to plug these values, these test values, into the second derivative. All right, again, you don't need to worry about these two because they're always going to generate positive values. So just worry about this one and this one. All right, so if you plug in a negative 2 into this x, you get a positive. And if you plug in a negative 2 for this x, you get 4. 3 minus 4 is a negative. So you get a positive and a negative, which is a negative. Plug in a negative 1 to the only two expressions we are worried about, again, because these two are going to yield positive results regardless of what x is equal to. So you're just looking at these two components of the second derivative to figure out the sign based upon this test value. So that's a plus 2, and this is going to be plus 2 as well, so it's going to be a positive. And this is going to be a negative times a positive, which is a negative. 2 is going to be a negative times a negative times a negative. That's going to be a positive. So there are your signs. And now what we need to do is come up with our conclusion. So therefore, f is concave what? Concave downward? Where? Concave downward on these two intervals, negative infinity to negative radical 3, or from 0 to positive radical 3. The function f is going to be concave upward. This is the happy face, on these two intervals, wherever they're positive, negative radical 3 to 0, or from radical 3 to 0. And that's it. A lot going on in this problem because of the algebra involved. Not easy. Stay with me. Example number 3, same directions, determine the intervals where the graph of the function is either concave upward and concave downward. So what I'm going to do here is I'm going to recognize that this is the same as 1/2 times the quantity of e to the x minus e to the negative x. I just pulled out the 1/2 in front, okay? Non-calculus move, just algebraic. All right, first move, same as it always has been. Figure out the first derivative. So constant multiple rule says we leave the 1/2 in front. And what's the derivative of this expression then? Well, the derivative of e to the x is e to the x. The derivative of negative e to the negative x is what? Well, it's this whole thing, negative e to the negative x, times the derivative of this exponent, which is negative 1. So the derivative of so the derivative of negative e to the negative x is negative e to the negative x times negative 1, which becomes positive e to the negative x. And then the second derivative, well, this is going to be interesting, isn't it? I think it's going to be interesting. The second derivative is going to be equal to what? Well, the derivative of this is e to the x. The derivative of e to the negative x is e to the negative x times negative 1, because negative 1 is the derivative of this exponent. Therefore, the derivative of e to the negative x is negative e to the negative x. Guess what? You're right back where you started from. That's what I think is interesting. All right, now what do? With the second derivative equal to 0, and we try to solve for x. Wow, this looks fun. All right, again, I told you, 10-2. It's a fun section. All right. I'm going to multiply both sides by 2. That's going to cancel up 2's there. You get 0 equals e to the x minus e to the negative x. I'm going to add e to the negative x to both sides. I'm adding e to the negative x to both sides. Oh, this isn't that bad, is it? This isn't that bad. Remember the property that states if we have like bases, we do what? We set the exponents equal to one another. Okay, it's the one-to-one property. So here we go. Negative x equals x. So what do we do now? I'm going to add an x to both sides. I'm going to add an x to both sides, perhaps, or you could just look at it and come up with the answer. But I'm going to add x to both sides, then divide both sides by 2. Bottom line is you get x equals 0. X equals 0. Okay, so we're going to look at the sign of f double prime like we've always done. And then we got to come up with test values in order to come up with that sign. So put your x value on your number line. Let's come up with test values, maybe -1 and maybe +1. All right, so we got to plug these into our second derivative, right? We're looking for the sign of f double prime, second derivative. So I'll actually show you this one. So f double prime of -1 is going to be 1/2 times what? E to the -1 minus e to the +1, right? If I replace the x's with the -1 in the second derivative, I would get this. Well, this means the same as 1/2 times 1 over e minus e. E is greater than 1 over e. So because you're looking at a smaller number and then minus a larger number, the difference here will be negative. Okay, so this is going to be negative. And then, you know, if you wanted to look at this one as well, the opposite's going to be true. We know this is going to be positive, right? Because, well, we're looking at a +1 here. Look, e to the 1 minus e to the -1 is what you'd get for f double prime of 1, which is the same as a larger value, in parentheses, a larger value minus a smaller value. Larger minus smaller gives you a positive. Okay, so our conclusion would be what? This function f is concave what? Concave downward. Downward, remember downward's sad face. Downward where? Negative infinity to 0, okay? And it's going to be upward. Where? Positive from 0 to infinity. And that's the work and the conclusion for number 3.